Okay, we're going to continue with the method of partial fraction decompositions, and on this one you'll notice we have a degree 2 polynomial up top, degree 3 on the bottom, so it is in the form. Degree of the top is less than the bottom. What we need to do is we need to factor the denominator though, so let's just look at the partial fraction decomposition here. Don't worry about factoring the numerator. Factoring the bottom, what? Greatest common factor is x squared. That leaves me an x minus 3. Okay. Now, what kind of factors do we have down here? Well, x minus 3 you're going to say is linear. Now, x squared, some of you might say that's a quadratic factor, but it's really not. It's really linear factor that's squared. In other words, this is, you can think of it as x minus or plus 0, doesn't really matter, quantity squared. Okay. It is a linear factor squared. Now you could treat it actually as a quadratic factor, but we're just going to treat it as a linear factor. And so what I have now here is for x squared, I have one linear factor squared, so I've got two fractions from that, right? So I'm going to have an a over x plus a b over x squared. Okay. Now, I'll just have you note, if you thought of that as a quadratic factor, you can combine these two as one fraction. You would need to multiply top and bottom of this by x, right? You'd have ax over x squared. You'd have what? Ax plus b over x squared. You're right back to that quadratic factor form. So we want to break that down a little further, and so this is the way we can do that. All right. X minus 3, is another linear factor, but there's only one of them. X minus 3 is the first, so I'll just have a third fraction from that again. So I have to find a, b, and c. Again, a, b, and c, any real numbers. Could be 0, some of them, potentially, but we know how do we go about finding these. So again, I'm going to multiply by the least common denominator. And the least common denominator, again, it's always going to be this denominator here, because all of these, again, are already factors of that denominator. So it's just multiply everything by x squared times x minus 3. Okay, so when I do that, what happens? Multiply this side, I just get the numerator. And on this side, what happens? I multiply a over x. One of these x's cancel, and I'm left with x times x minus 3. So it's a x times x minus 3. Here, the x squared cancels, left with x minus 3. And then here, the x minus 3 is canceled. I'm left with c x squared. Okay. Now, we could use the shortcut that I used in the previous video on the first problem we did, by letting x be 0 and x be 3. Okay, if x is 0, then essentially the a and c are gone, right? And I can solve for b. If x is 3, the a and b are gone, and I can solve for c. But what about a? How am I going to solve for a? So that's a problem we need to address, and I want to look at this in general, because if you have more fractions, you'll have more of these, and the little shortcut I showed doesn't work to solve for all or maybe any, depending on the situation of those variables. So I want to look at a method known as the method of undetermined coefficients now. And it's a method that's helpful in other settings as well, other problems in mathematics. So let's take a look at it. We've got a polynomial here, and we got a polynomial here. What we're going to do is we're going to sort of match up the coefficients of what our x squared term coefficients have to be 3 here, right? 3x squared. Coefficient of x has to be -10, and the constant is -6, and so that has to be true over here as well. So what I'm going to do is I'm going to expand this out and combine like terms. I do have a capital A, B, and C. Those are unknowns. They're going to be real numbers we're going to find. Of course, x is a variable. So I've got ax times x is ax squared. ax times a negative 3 or minus 3ax, right? Distribute that ax through. Here, distribute the b through. I get bx minus 3b, and of course my cx squared. Now I'm going to combine like terms. Okay, how do I do that? What are like terms? In the variable x, right, I get x squared and x squared. So the coefficient here, a, and the coefficient here, c. How do I combine like terms? I add those coefficients together. Right, a plus cx squared. What about the x terms? I've got two of those, which will be what? Negative 3a plus b times x. And then I have a constant term, negative 3b. Okay, and so the method of undetermined coefficients says, okay, we have to have the coefficients match. In other words, the a plus c has to be what? For these to be equal, a plus c has to be 3. Do you see that? A plus c has to be 3. And the coefficient in front of x, negative 3a plus b, has to be what? Negative 10. And the constant term has to be negative 6. Does everyone see that? So that's the only way these are going to be equal. And so what we get in the method of undetermined coefficients is what we call a system of linear equations. There are 3 equations here in the unknowns a, b, and c, and we can solve that system. Okay, and so in general there are techniques, but this one comes out pretty easily because right down here we would probably start and say, hey, this last equation there's only a b in. I can solve for b by what? Dividing both sides by what? Negative 3, and I get b is equal to 2. That's pretty easy. And then once I know b, everything else begins to fall into place. So now I can come here and say, well, if b is 2, I got negative 3a plus b. Well, that's just plus 2 equal negative 10. I can now solve for a, right? So if I subtract 2 from both sides, I get negative 3a equals negative 12. And so I get a is positive 4. And now I can say what? If a is positive 4, I can come here and say a is 4 plus c must be 3, and therefore I know c is what? Negative 1. So a lot of times the system of linear equations comes out to be fairly easy and straightforward to solve. Now, it is possible that it's not so straightforward, and you might have to, if you have like a c, maybe this was c minus 3b equals negative 6. Then what you got to do is sort of solve both equations for a particular variable and substitute into the other equations, and thereby creating one equation with one unknown is what your goal is, like we have here, and then kind of back substitution, if you will, going back and finding the other variables. So there are techniques. You can take a whole course with me called linear algebra, and we'll look at all sorts of methods for solving, looking more in depth at the process of solving systems of linear equations, especially when you have a lot of equations and a lot of unknowns. Okay, but for most part, we're going to be able to do this. Some of you know how to do that and know how to use matrix methods or have a program in your calculator to do that, but make sure that you're able to solve these systems and set these up. Okay, so with that, we can now, what are we doing here? Let's go back. I know a, b, and c. What are a, b, and c? Those are the numerators of these fractions. So this whole fraction can be now written this way, more broken up into smaller pieces. Notice I could not find the antiderivative directly just by u substitution. This is not the derivative of the denominator up top, so I don't get 1 over u du on this whole thing. Otherwise, if I could, I wouldn't go through this whole process. But now I can rewrite this as, so let's do that. I can rewrite this thing as the integral of what? A over x, where a is 4, so that's 4 over x, plus b over x squared. B is 2, so plus 2 over x squared, and then plus c over x minus 3. C is negative 1, so plus that, I'll say minus 1 over x minus 3. And again, you can check, you can combine these fractions as one, and you should get back to the original expression. So we're not changing anything, but we are making it easier to evaluate. All right, so what do we get of the antiderivative? What's the antiderivative of 4 over x? The 4 is a constant multiple. What's the antiderivative of 1 over x? The natural log absolute value of x. Okay. Be careful. What's the antiderivative here? Is this a log integral? Does this evaluate as something log of something? No. It's not 1 over u. This is what? This is 2 times x to what power? 2 times x to what? The negative 2 power. This is just straight up power rule. Okay? What do we do? 2 is a constant multiple. Add 1 to the power. I get negative 1 divided by negative 1. So just as a recall, right? The antiderivative here of 2 over x squared by itself is the antiderivative of 2x to the negative 2, which is 2. What? I add 1 to negative 2, I get negative 1 divided by negative 1, right? Which is 2 divided by negative 1 is negative 2, and x to the negative 1 is 1 over x, so it's negative 2 over x. Okay. And so minus 2 over x. So it's not a log, doesn't value. So we get a lot of logs, evaluated, but not always. Okay. What about this one? Well, now this is logarithm, right? If I let u be x minus 3, du is dx, I get 1 over u. So the antiderivative is natural log absolute value, right, of u, which is x minus 3. And there's our antiderivative. There's our antiderivative. Okay. Now, this next one is going to require long division. And the reason is, look at the degree of the top. It's 3. Look at the degree of the bottom. It's 2. The degree of the top has to be less than the bottom in order for partial fraction decomposition to work. We can't do it like we've been doing until we do polynomial long division. So you remember how to do long division, polynomial long division? It's based on the same as regular long division. Suppose I have, if I want to know what 321 divided by 7 is. What's 321 divided by 7? Well, I have to, you say, oh, use my calculator. Well, remember this thing? Remember long division? 7 goes into 3. Well, it doesn't. 3 is too small. 7 goes into 32. Yeah. How many times? 4 times. And we put the 4 right above the 2 here to the far right, right? 4 times 7 we multiply is 28. Now we subtract 32 minus 28. That's 4. Now what? We bring down, right, that 1. 7 goes into 41. Was that 5 times? 5 times 7 is 35. 41 minus 35 is 6. That's my remainder. And so what do we write this? We write this as 45 plus a remainder of 6 over 7 plus 6/7. That's the way we write that. Sometimes we write this as a mixed number, which is a little confusing. Notice when I write 45 and 6/7, that's not 45 times 6/7, it's 45 plus 6/7. So be careful that you understand that. In other words, we're saying 7 goes into 32 45 times with a remainder of 6 left over. And I can see that because if I multiply both sides of this equation, by 7, right, this is the real important thing, then I get what? 321 equals 45 times 7 plus 6. And that really shows what's going on here. Right, 7 goes into 321 45 times, so 45 times 7, and then there's 6 left over. Add 6 more, you get to 321. Okay, but this is the process I want to do with the long division here. And so here, the divisor was 7. Here, it's x squared plus 3x plus 2. Put that in descending order. And by the way, if we have any missing powers of x, we need to put in a placeholder to line things up. It's real important. Say I'm dividing 7 so say I'm dividing by 101. If I wrote 101 out here, I wouldn't just write 1, get rid of the 0. That 0 is a placeholder for the tens place, so we need it. Same thing here. If I had just x squared plus 2, I would want to put in a 0x there as a placeholder. Just lines everything up as it should be. Divided into what here? 321 here. Same thing. This what we're dividing into is sometimes called the dividend, the numerator here. Put that in descending order. Again, if there are any missing powers of x, we want to put in a placeholder. Okay, and how do we divide here? Well, here we had to get 7 into 3. That didn't work. 7 into 32. It's got to be big enough, so to speak. Here, it's easy. You have 1, 2, 3 terms. We go into 1, 2, 3 terms. And how do we do that? We take the highest degree term and divide it into the highest degree term, which should be the first terms, right, each time, because we put them in descending order. How many times does x squared go into 2x cubed? Answer, 2x times, because 2x times x squared is 2x cubed. Where do I put that 2x? Well, just like here, remember we put it over to the far right. We're going to put it to the right of what? The 3 terms. And notice when we do that, it's 2x, and it's in the same sort of column as 9x. Everything in this column is going to have x. Everything in this column is going to have x squared. Everything in this column is going to have x cubed. That's why it's real important to put placeholders in. Line everything up. Now what? I multiplied 4 times 7 to get 28. Here I multiplied 2x times this polynomial, which means I have to distribute. 2x times x, 2x cubed. 2x times 3x plus 6x squared. 2x times 2 plus 4x, right? And now what? We subtract. Be careful subtracting. 2x cubed minus 2x cubed is 0. 6x squared minus 6x squared is 0. 9x minus 4x is 5x. Bring this 13 down. Now what? X squared into this. Well, notice the degree of this now is greater than this degree. What we're dividing into can't be done. You can divide if the degree is equal or what you're dividing into is more, like we were doing with this from the start. So this is the stop, right? So here, same thing. I can't go into 6 anymore, and there's nothing more to bring down, nothing more to bring down here. So we're going to say what? We're stopped. That's the remainder. That's the remainder. So how do we write our answer then? Just like we did up here, the answer is our quotient, right? Plus what? The remainder over what? The divisor. And so this is going to be the integral of 2x plus 5x plus 13 divided by what? Our divisor, which was x squared plus 3x plus 2. Okay. Now, what we have here, we can now note that the degree of the top is 1, the degree of bottom is 2. So here, again, to evaluate, I'm going to use partial fraction decomposition on this part. If I let u be x squared plus 3x plus 2, du is 2x plus 3. That's not a multiple of 2x plus 3, so I have to do the partial fraction decomposition. Here, the antiderivative of this is easy, right? What's the antiderivative of 2x? That's x squared. Okay, so here we do partial fraction decomposition, and let's do that real quick. I got 5x plus 13. Factor that. That's going to be x plus 1 times x plus 2. So the decomposition is a over x plus 1 plus b over x plus 2. And again, I'm going to multiply both sides by the denominator, x plus 1 times x plus 2, which gives me 5x plus 13 equals a times what? The x plus 1 cancel, leaving x plus 2. Here the x plus 2 cancels, leaving x plus 1. And now I'm going to use my shortcut. I only have linear factors, so I can do that. I'm going to let x be negative 1. I get negative 5 plus 13 is 8. And here I get negative 1 plus 2 is 1. I get a is 8. And this is 0. When x is equal to negative 2, negative 2 times 5 is negative 10 plus 13 is 3 equals 0. And then plugging in negative 2 here, negative 2 plus 1 is negative 1. I get negative b, and so b is just negative 3. And so this becomes the integral of what? A, which is 8 over x plus 1, plus b, or minus b is negative 3, so minus 3 over x plus 2. And that's going to be equal to 8 natural log x plus 1 minus 3 natural log x plus 2. Okay. So going back to the original, so that's just this part here, right? There's the evaluation of the partial fraction decomposition. So therefore this thing here is equal to what? Antiderivative of 2x, which is x squared, don't forget that, plus, right, all this stuff, 8 natural log absolute value of x plus 1, and then minus 3 natural log absolute value of x plus 2, plus c. Okay, lots of fun, lots of fun. We're going to do in the next video some examples where we get quadratic factors in the denominator. So far we've only had these linear factors in the denominator. What happens when we have quadratic factors? Ooh, it's going to be exciting. We're going to do that next.